Let's just take a few moments and review what we had discussed in the past three videos, videos 8, 9, and 10. In video 8, we had discussed carboxylic acids, and here we have just a generic carboxylic acid. And we noted in video number 8, when the proton dissociates, in other words, this being an acidic compound, carboxylic acid, obviously it's acidic. So when it loses the proton, we have the anion here. And the anion is stabilized by a strong resonance system. And this is, of course, what we went over in video 8. Here is the resonance. Now, the reason why it's so strong is unlike what you saw in some of the other videos, there's no charge separation. For example, there's no positive charge here and then a negative charge here, or maybe a positive charge here and a negative charge somewhere else. And also, when we consider the different Lewis structures, the different canonical forms, we have charge dispersion. Here, this oxygen has a negative charge. Then in the other canonical form, this oxygen has the negative charge. And that type of charge dispersion, again, helps make a resonance system. It helps make it more stable, more effective. Also, these different canonical forms are symmetrical. You can imagine if we just rotated this carboxyl group 180 degrees about this bond, then this would be up here and this would be down over here. So there's a symmetry between these canonical forms, and that symmetry imparts even more stabilization. Now, in terms as to what the anion actually looks like, again, we don't mean to imply when we have the double arrow here that it's going back and forth, shifting back and forth between these two forms, where here we have a double bond, then it's a single bond, then it shifts back to a double bond. That's not what we're trying to represent in these different canonical structures. The situation is more like this. This is the anion now. So the oxygen with the negative charge, we should have pointed out that these are a lone pair of pi electrons. And again, we had discussed the structure and the hybridization of both the carbonyl oxygen and the hydroxyl oxygen back in video number 8. But here then we're showing the lone electron p orbital pairs. So where this is depicted right now, that would have a negative charge. And then we have the carbon and the carbonyl oxygen. Now, while it was protonated, while it was in this form, this was a double bond. So the pi orbitals between the carbon and the oxygen were actually overlapping to form that pi bond. Now, in the anion, it's a bit of a different situation. What we have is the oxygen with its lone pair of pi electrons, the carbon with its single electron in the p orbital, and the carbonyl oxygen with its single electron in the p orbital. And notice we're not drawing where these p orbitals overlap anymore in a pi bond structure. What is happening instead in the anion is that these 1, 2, 3, 4 p orbital or pi electrons, these are shared amongst all 3 nuclei. And that's what we mean when we talk about the electron delocalization and resonance in the p orbitals, the pi electrons, that these 2 electrons from oxygen are not just restricted to this p orbital. All 4 electrons are sort of shared amongst all 3 atoms, the two oxygen atoms and the carbon atom. So what you have is not real bonds that are being formed, but it's like a bond strengthening effect. So this is what we're trying to show in the Lewis diagrams, that here it's no longer a double bond between the carbon and the oxygen, and that's why we're showing it first like this and then like this. This is no longer just a single bond, so that's why we're showing it in the two forms here. Obviously, this is a much better representation of the physical situation, but as we discussed in the previous videos, it's useful to write out the different canonical forms, because a general rule is the more canonical forms you can write, then the more stabilized the system is through resonance. And the reason being is the more canonical structures you can write out, that then is an indication that there is more delocalization of the pi orbital electrons that are sort of being shared amongst multiple nuclei. And again, it's not a genuine bond, but it does have like a bond strengthening effect. Now, going back to the carboxylic acid, before it lost the, let's just go back to here. So when we're drawing the Lewis structures, it's like an exercise in how we can shift the different pi electrons amongst different atoms. All other bonds remain the same. So when we're drawing the Lewis structure here, we're supposing, well, here's a pi bond, so the carbon and the oxygen are each sharing a pi electron between them. This contributes a pi electron to the bond. That contributes a pi electron to the bond. They're being shared amongst them. Now, when we're drawing the Lewis structures, we're trying to imagine, and of course, this has a lone pair of pi electrons, so how can we shuttle these about? So we could imagine, well, perhaps this oxygen might keep both of the pi electrons for itself. It literally swipes one from the carbon atom. That's how we show it here at the negative charge. This now then lost a pi electron. This bond is gone. But here we have these lone pair pi electrons. So you imagine them sort of swooping down and being shared between the carbon and the oxygen to form that pi bond. That effectively means then that this lost an electron. It has a pair here, but it's donating them to form this bond. Carbon isn't donating any electrons, so normally this would have a positive charge, but a negative charge to begin with, so it's neutral. So that's how we form the different canonical structures then. It's just imagining different ways that we can shuffle the pi electrons amongst the different atoms. That is, the atoms that are adjacent to each other, that have adjacent p orbitals that can participate in this system. Now, if we go back to the protonated form of the carboxylic acid, again, it's the same exercise. As we pointed out in video 8, the hydroxyl oxygen is hybridized, so it has a lone pair of pi electrons. Of course, here we have the pi bond in the carbonyl group. So again, we imagine these pi electrons, both of them going to oxygen, so has a negative charge, no more pi bond, just the single bond. And then these lone pair of pi electrons coming in to be shared between carbon and oxygen, giving the oxygen a positive charge. Carbon remains neutral because when a lost electron from here being stored by that oxygen, it would have a positive charge, but it gains one from this oxygen, so that doesn't have any charge on it. So here, with the original compound that is in protonated form, there is some resonance stabilization of this, but it's not as good as this resonance stabilization for two reasons. We have separation of charge. That is not ideal. It is permissible, but not ideal. And so here we have charge dispersion instead of separation of a positive and a negative charge. And then here we also have symmetry. So the original form of the carboxylic acid, the protonated form, it is somewhat stabilized. And of course, if it was stabilized strongly, say through resonance stabilization, then it would just be a very inert, stable compound. But in fact, when it loses the hydrogen to form this anion, the resonance here is so much more effective. Therefore, the carboxylic acid is very motivated to shed that proton, form the anion, and have this superior resonance. Now, what happens instead of having an oxygen here, we have a nitrogen. This is an amide. Now, before we discuss that, let's just briefly review what an amine is. And that's just simply a nitrogen attached to some functional organic group, two hydrogens, and a lone electron pair. This we discussed in video number 9. But this nitrogen here is sp3 hybridized. And this lone electron pair are sp3 electrons. So there's no chance of it participating in any resonance. Only p orbital ones can participate, the pi electrons. So that means that these pair of electrons are available to hook up with any protons that might be in our system, meaning that the amine nitrogen is basic. Now, notice that in the amide, again we have a nitrogen with 3 bonds, 2 of them to hydrogen, and 1 going to an organic group, in this case a carbonyl carbon. But this nitrogen, as we discussed in video number 9, this is not sp3 hybridized. This is sp2 hybridized. So these lone electron pair right here, these are pi electrons now. And what that means is that, again, we can have a resonance system set up. So that it's what we did before with the carboxylic acid. We can imagine the oxygen taking both pi electrons, giving it a negative charge, and then these lone pair of pi electrons being shared between the carbon and the nitrogen to form that pi double bond. But the nitrogen has a positive charge because it donated both electrons to form that bond. So here, if we look at this, again, we have a resonance stabilization of the amide. And we'll talk about this in more detail in a few moments. But what happens if this loses one of the protons? So that we have an anion here. Now, the lone pi electrons, those are still there. Now what happens if we try to form a Lewis resonance structure with this? Again, we imagine the oxygen acquiring both pi electrons. It has a negative charge. This pair of pi electrons comes in to form the double bond. But now nitrogen does not have a positive charge when it donates both electron pairs, because it had a negative charge to begin with when it lost that proton. So again, we see that when the amide loses a proton, in other words, when it acts like an acid, it's acidic, it forms this anion, and this anion has a better resonance stabilization than the protonated form. So unlike amines, amides are somewhat acidic. And again, it's because of the superior resonance of the anion that's formed when this nitrogen loses a proton. We have charge dispersion instead of charge separation. Now, if this is true, our amides are they as acidic as a carboxylic acid? And the answer is no, and there's like 3 reasons as to why. First of all, notice that when the carboxylic acid, when this sheds the proton, we have an oxygen with a negative charge. When the amide loses a proton, we have a nitrogen that has a negative charge. Oxygen is more electronegative than nitrogen. It can accommodate the negative charge better. So that's reason number 1. Reason number 2, the carboxylic acid anion has a symmetry in the resonance structures that exist. No such symmetry exists here, so this has a better resonance stabilization than this, meaning that the carboxylic acid is more motivated to lose the hydrogen than the amide is. Therefore, the carboxylic acid is more acidic than the amide. And reason number 3, if we go back now and look at the protonated form of the carboxylic acid, we saw that we can write a resonance structure, but it's not, the resonance here is not nearly as good as the resonance here, so it's still motivated to lose that proton. But let's compare this resonance of the protonated carboxylic acid with the resonance of the amide, this. And here we have charge separation. Here we have charge separation. Again, not ideal but permissible. But here when we have the charge separation, the positive charge is on the nitrogen. Here it's on the oxygen. Again, nitrogen is less electronegative, so this having a positive charge as opposed to the oxygen is a more ideal situation. What's more, of course, we're dealing here with electron delocalization with these pi electrons. Nitrogen is less electronegative than oxygen, so it's easier to delocalize these pi electrons than what it would be for oxygen. So what it means is that the protonated form of the amide has a better resonance stabilization than the protonated form of the carboxylic acid. That would mean then that this would be, if it's more stabilized through resonance, this would be somewhat more inert then. It's more stable than this, therefore it's somewhat more inert, which means then that it's not as active, so it's not going to lose this proton quite as readily as what this does, because this is not an altogether bad resonance situation here. So 3 reasons why an amide then is not as acidic as a carboxylic acid. The negative charge is on the oxygen. Here it's on nitrogen, less electronegative. Very good resonance stabilization here. Not as good here because there's no symmetry. And finally, this might be a little bit more stable because of this resonance situation than this, meaning it's not as reactive, so this is not going to be as motivated to lose a proton as what this is. And then finally, actually we talked about amides in video number 10. If we said number 9 before, we misspoke. It was video number 10 when we discussed the amide system. What we discussed in video number 9 is the fact that this carbonyl oxygen has 2 lone electron pairs, and as we discussed in actually video number 9 now, these are sp2 electrons, and actually as we discussed in video number 9, the hydroxyl oxygen also has a lone pair of sp2 electrons as well as the pi electrons. So if it exists like this, is it possible then to protonate the carboxylic acid? In other words, can the carboxylic acid function as a base? And as we point out in video number 9, first of all, we would never protonate the pi electrons if they're available to be delocalized, because if we attach a proton here, these would not be available for resonance. So if you're considering about protonating a compound, usually it does not happen with the pi electrons if they can be set up for a resonance system, because that would destroy any chance of forming resonance. What we pointed out in video number 9 is that we can put a proton on one of these sp2 electrons, and in fact, the carbonyl oxygen and carboxylic acid is more basic than the carbonyl oxygen of an aldehyde or a ketone. And again, we explained that at some length in video number 9. Now, let's go to the amide. This too has sp2, a lone pair of sp2 electrons, 2 of them. So is it possible also to protonate an amide? So the amide would be somewhat acidic, and maybe it's basic as well. That we will examine in the next video. Can you protonate this carbonyl oxygen just as we did with the carboxylic acid? And we'll turn to that problem in the next video. A reminder that the playlist for all the videos is at the website digital-university.org.